Good morning and welcome to the video course on advanced hydrology. We started the well hydraulics in the last class, in which we looked at what goes on inside an aquifer when we pump the water out of the aquifer. Okay. And we looked at the two cases of confined and unconfined aquifer. The dynamics is slightly different, because in the unconfined aquifer the water comes out of the storage, whereas in the case of the confined aquifer the water is coming from the recharge areas. Then we looked at the derivation of the equation for pumping discharge Q towards a well in the confined aquifer, all right, and we assumed a very simplified case of radial flow which is steady in a confined aquifer which is homogeneous and isotropic, and the flow is incompressible and so on. Okay. We derived that equation, and what we would like to do today is look at an example for the confined case and then look at the derivation of the similar equation for the unconfined aquifer, and then look at an example for that, and then we will move on from there. Okay. So, I would like to get started with looking at an example of confined aquifer radial flow into a well. So, in this chapter, that is example 3, and it goes like this: a 30 centimeter diameter well completely penetrates a confined aquifer. A confined aquifer with hydraulic conductivity K given to us as 45 meters per day, which is quite high. The length of the strainer, okay, is given to us as 20 meters. What is a strainer? Well, strainer is a casing, all right, in the confined aquifer through which the water gets filtered, or all right. So that no sand or debris is coming in. So, basically that is what is this length of strainer is representing is the thickness of the aquifer equal to B. Okay. Other data, other information that is given is that the under steady state pumping, the drawdown at the well at the pumping well, that is SW, right, was found to be 3 meters, okay, under steady state conditions. Assuming your radius of influence as 300 meters, find out what is the rate of pumping. Okay. So, these are the data given, all right. It is a very simple problem in fact, all right. So, let us see how we can find out this discharge or pumping rate Q. Okay. It is a good healthy practice to write down all the data first. Okay. The diameter is given, the diameter of the well. So, the radius at the well will be half of that. So, which is 0.15 meters. Okay. The radius of influence capital R is given to you as 300 meters. Okay. So, now you know that which data you are going to use. Well, your first cross section will be at the radius of influence and the other one will be at the well itself. Okay. So, 1.1 and 0.2 are at the radius of influence and at the well. The drawdown at the well is 3 meters, okay, and drawdown at R obviously is 0. Okay. So, we are not writing that. B is equal to 20 meters, K is 45 meters per day is equal to, you can convert it into meters per second. We want to find out the things in let us say in SI units. So, you have 45 times 1 over, it will be 24 hours times 60 times 60, okay, number of seconds in a day. So, it is going to be 5.208 times 10 minus 4 of your meters per second, okay. And you can calculate the capital T, which will be K times B, okay, and it is 5.208 10 minus 4 we just found out times 20, okay, B is 20. So, it will be 10 times 416 times 10 minus 3 meter square per second, okay. So, you can do these computations fairly easily. For the steady radial flow in confined aquifer, we derived that equation in the last class. What is Q? It is 2 pi T SW, all right, S2 minus S1. So, S2 is your SW, S1 is 0, divided by natural log of what? R2 over R1, which is capital R over RW, okay. So, we have calculated T, SW is given, R is given, RW is given, pi is a constant. So, if we put all the values, we can find what is the value of Q. So, it is going to be 2 pi times T is 10.416, 10 minus 3, it is meter square per second, times drawdown at the well is SW is 3 meters, this whole thing divided by natural log of capital R is 300 divided by radius at the well is 0.15, everything is in meters here, okay. This will come out to be 0.02583 meter cube per second, okay. Everything is in SI units. So, your discharge is going to be in meter cube per second, okay. We can convert this discharge into other suitable units. You multiply by 1000, what is that? That is liters per second, because there are 1000 liters in a meter cube. So, what is that? 25.83 liters per second, okay. If you want, you can convert it into some other units, 2583 times 60, okay. That will be what? Liters per minute, right. So, that is approximately 1550 LPM, okay. Therefore, you say that your discharge coming out of that pumping well in the confined aquifer is 0.02583 meter cube per second, or 25.83 of your liters per second, or 1550 liters per minute, okay. Or we can express this in any other suitable units we want. So, that is your answer, okay. So, this way we see that it is a very simplified or very simple numerical example of calculating the discharge or the pumping discharge coming from a well in a confined aquifer under steady state conditions, okay. We have not looked at the unsteady case, which we will do little later in this course. Now, what we will do is we will move to the unconfined aquifer case, okay. We will apply the similar analysis which we used in deriving the expression for Q, okay. So, let us do that first and then we will see an example. So, the second case we are looking at is steady radial flow towards a well or to a well, and we are looking at unconfined case. Okay. All right. As we had seen earlier, when we were deriving the governing differential equations for the unconfined aquifer, all right, the main problem there is that the streamlines are not horizontal, okay, and parallel to each other. That is a problem in the unconfined aquifer. Okay. So, what we do is we simplify our analysis and we say that we are going to use the Dupuit's assumptions. Okay. So, for the case of well hydraulics also, what we will do is we will employ or we will use this Dupuit's assumption. Okay. So, the solution which we are going to get will be under the these assumptions. So, let us look at the schematic diagram of what is actually happening. So, you have the horizontal impervious bed as usual, okay, and then you have the well which is penetrating completely. This is your ground surface, okay. The discharge that is coming out is Q from this well. This is twice of RW. To start with, initially this is, let us say, your original groundwater table, okay, and under the steady state conditions it will drop and a cone will get formed and you will have this as your groundwater table under pumping, okay, and this is under the steady state conditions, okay. All right. So, let us define all the parameters like we had done earlier. So, everything we are going to measure from the center of the well, all right. This is your capital R, okay. You are going to take a couple of observation wells. So, let us say this is your S1 and this is your S2. The corresponding values of the height of the groundwater table are going to be H1 and H2 from the bottom of the aquifer, okay, and these things are located where? At R1 and at R2 from the well, okay. At any general distance, let us say this is your S and this is your H as a function of R, okay, and this is your R. The height in the well is HW and this is of course your SW, okay. All right. So, what we will do is then we will employ exactly the similar analysis. So, what we will do is, if you look at from the top, you take a cylinder of radius r, okay, and then we will apply the Darcy's law to this radial flow, okay, which is taking place towards the well, right. What would that be? Well, it will be Vr is the radial velocity, which will be k times dH dr, okay, like we had said earlier, right. Now, what will be the pumping discharge? This Q is going to be equal to your the velocity times the area, right. The velocity we have said is k dH dr as per your Darcy's law, and what is the area of cross section across which this flow is now taking place. Earlier we had the cylinder of height b, and now at any distance r, what is the height of that cylinder? It is h, this one, at any general distance r, all right. So, the area, the cross sectional area across which this radial flow is occurring is going to be 2 pi r times h, okay. 2 pi r is the circumference, h is the height, okay. So, that will be the cross sectional area of your cylinder if you open it out. Once we understand that, the remaining thing is simple mathematics. So, you separate the variables like we had done earlier. then you will have dr over r on the left hand side, and then on the right hand side you will have h dh. Okay. And if you integrate on both the sides, integration will give you the equation of q, all right, and integration we are doing between locations 1 and 2, okay, which are corresponding to your r1 and r2. Okay. So, once you do that, your expression would come out to be pi k times h2 square minus h1 squared over natural log of r2 over r1. Okay. So, this is our relationship or corresponding relationship for the unconfined case, and we are going to number this equation as equation number 5. We can apply phi at the boundaries like we had done earlier. Okay. That is the radius of influence capital R and the well itself R w. Okay. Once you do that, what you will have is q is equal to pi k times h 2 is capital H minus h w squared divided by natural log of your radius of influence divided by R w. Okay. We have defined all those things earlier. I may not have written capital H. So, let me do that. This is your capital H. Okay. So, this way you see that the expression for the unconfined case involves H square, all right. While deriving the groundwater general flow equations, we had seen that the governing differential equation was a Laplace equation for the confined aquifer, all right. For the unconfined case, it was Laplace in H square for the steady state, and on the right hand side we had the recharge term, and the unsteady case we had the t term, dH by dt term, all right. So, we see that for the case of the well hydraulics also, the discharge expression involves simple H or H2 minus H1 basically in the confined case, but for the unconfined case we have a square of that, okay, because of that variation in the groundwater table. Okay. The next thing we will do is look up at an example based on this unconfined case, and then we will move on from there. So, the next example is your example number 4 for this chapter basically, and that is how it goes. A 30 centimeter well completely penetrates an unconfined aquifer of saturated depth of 40 meters. Okay. So, what is this? This is your capital H. Okay. After a long time of pumping, okay, so you are pumping water from the unconfined aquifer, and after a long time of pumping at the rate of Q is equal to 1500 liters per minute, okay, that is the yield from the aquifer. The drawdowns in the 2 observation wells, which are 25 meters and 75 meters from the pumping well. Okay. So, these are your R1 and R2. Were found to be were found to be 3.5 meters and 2.0 meters. So, what are these things? These are the drawdowns S1 and S2 at R1 and R2, this is given to us. and then we say respectively. Okay. Now, what we have to do in this problem is determine or find A, the transmissibility the aquifer parameter of the unconfined aquifer. That is number 1. Unconfined aquifer, and the second one, which is B, is the drawdown at the pumping well. Okay. All right. So, let us see how we can do this. Like earlier, let us list all the data that are given to us first. RW is 0.15 meters. Okay. Capital H is the height of the original or the groundwater table originally, which is given to you as 40 meters. Okay. The discharge is 1500 liters per minute. The radial distance from the pumping well of the first observation well is 25 meters, and similarly your R2 is 75 meters. The corresponding values of the drawdowns, S1 here is 3.5 meters and S2 is 2 meters. All right. Now, A, we want to find out T. Okay. Well, what we know is this for the case of unconfined aquifer, pi k H2 square minus H1 square over natural log of R2 over R1. This is what we just derived for the unconfined case, right, and we have to find the transmissibility, and transmissibility is what? Hydraulic conductivity times the thickness of the aquifer. All right. So, first we need to find K, all right, to be able to find the transmissibility. In this equation everything is given to us. So, Q is given, all right, H1, H2, R1, R2, these things are given to us. In the sense that the drawdowns are given, we can find out what will be the H1 and H2. Okay. So, you see that H1 is going to be what? Nothing but capital H minus S1, which is 40 minus 3.5, which is 36.5 meters. Okay. H2 is capital H minus S2, which will be 40 minus 2.0, which is 38 meters. Okay. And also you can say Q, you can convert it into meter cube per second, it is 1500 liters per minute. So, you can multiply this by 10 to the power minus 3 to convert it into meter cube, and minutes you have 60 seconds, right. So, this will be in meter cube per second, right, and this will come out to be 0.025 meter cube per second. Okay. So, now you have all the data, you can plug into this equation, all right, and get the value of K. All right. So, if you did that, you have 0.025 is equal to pi k of your 38 square minus 36.5 square, right, divided by natural log of this is R2 over R1, which is 75 divided by 25. Okay. Everything is in meters here. This will give you capital K as 7.823 times 10 minus 5 meters per second. Once you calculate that, okay, you can verify that. What will be TH? Sorry, the T will be K times H, right. For the confined case, it was K times B. So, it will be K times capital H for the unconfined case, all right, for the original condition. So, it will be 7.823 10 minus 5 of course, and multiplied by capital H is 40. So, you have 3.13 10 minus 3, the units are going to be meter square per second. Okay. So, that is part A, in which we find the transmissibility of the aquifer. Okay. Next, we have to find out what will be the drawdown at the pumping well, okay, SW. So, how do we do that? Let us move on. You have RW is equal to 0.15 at the well. Okay. Now, we use the same equation, which is Q is equal to pi k of your H1 square minus Hw square. So, it is H2 minus H1 basically, and H2 is H1 here, and the second one is at the well, right. So, do not get confused. So, you have R1 over Rw, okay, 2 by 1. We have all the values here, okay, except Hw, okay. If we find Hw from this, we can find the drawdown. So, you have 0.025 is the discharge, which is equal to what? Pi times the k we just found out is 823 times 10 minus 5, this is meters per second, and then you have 36.5 square, this that is H1 minus Hw, that is what you have to determine, divided by the natural log of R1 was 25, Rw is 0.15. Okay. So, from this equation you can calculate this guy here, okay, easily. If you did that, what you will have is this Hw square is 811.84. Please verify all these things, it will be square meters, or that will give you Hw as 28.49 of your meters. Okay. So, this is the height of the water table in the well. Okay. Once you have that, how do you find the drawdown? Well, this is capital H minus Hw. This was 40 and this is we have just found as 28.49 meters. Okay. So, that way you see SW is equal to 11.51 meters. Okay. That is going to be your answer. Okay. All right. So, we see that the case of the unconfined aquifer is slightly different and slightly more complicated, because it involves the square of your groundwater table. Okay. Nonetheless, the computations are very similar and simple, and we can use the derived expression for calculating Q, and if we know the Q, we can find out the drawdown or the height of the water table, etc. Okay. So, that this will help us in managing our groundwater resources. Okay. Up until now, what we have done is we have looked at a single well. All right. You have an aquifer, whether it is confined or whether it is unconfined, you have a single aquifer. Okay. Later on in this course, we will look at the multiple well case, in which you may have more than one wells. All right, and then you need to be able to calculate the drawdown and the groundwater table due to pumping. All right, from one aquifer from one pumping well, what will be its effect on the other pumping well. All right. So, we are going to look at those things little later. But before we move on to that, what I would like to do is I would like to look at the case of unconfined aquifer when there is a recharge. Okay. Until now, we looked at the steady state case of pumping the water out when there is no recharge is happening. All right. However, we may have a situation in which the rain is also taking place and you are pumping water out also. Okay. In that case, you have certain amount of recharge taking place, and the dynamics in the aquifer groundwater flow will be slightly different. Okay. So, let us look at that. So, now we are looking at the unconfined aquifer with uniform recharge. Okay. Okay, so let me first draw the figure and then we will look at the dynamics. This is your horizontal impervious bed, as usual. Then you have this is your pumping well, okay, and this is your ground level. Okay, you are pumping at the rate of QW. QW we are representing as a discharge at the well. Okay, and let us say this was your original groundwater table. Okay, after some time you will have groundwater table would be like this. Okay, that is your groundwater table under pumping. Okay. Now, what is also happening is there is a recharge taking place into the aquifer from the top, okay, and the rate of recharge is, let us say, W. Okay. Now, it is important to see that if we did not have any recharge, without recharge, the Q at the well is equal to Q in the aquifer anywhere. That is what we had used. Okay. So, what we are saying is that if you have no recharge taking place, then what discharge we are pumping out, the Q from the well, that is equal to the discharge, all right, that is taking place anywhere in the aquifer. In fact, that is the equation we had used, all right. Q was velocity times area. We used the Darcy's law and found out the cross sectional area, all right. So, that is the concept we had used. Now, there is an additional mass flux entering in, all right, due to the recharge. So, the water which we will be pumping from the well actually will not be equal to or will not be same as the discharge that will be taking place at any point in the aquifer. Why is that? Because there is an additional input, all right, additional amount of water that is going in and contributing to the storage of your aquifer, unconfined aquifer, and this discharge which is, or this recharge basically will contribute certain amount of flow towards the well when we are pumping out. So, as we go away from the pumping well, all right, so as R is increasing, the amount of discharge in the unconfined aquifer will be varying or it will be different. Okay. So, this is very important to realize that. So, once we do that, so let us say, but with recharge, let me rephrase what we are trying to say. The recharge value is W, the discharge at the well, what is that? QW actually is going to be the highest, okay, and Q in the aquifer at any location will be function of R. As I said, it will be varying in the aquifer. Okay. As one approaches the well, or as we go towards the well, this Q increases because of the recharge that is taking place, because you have additional water going in. So, that will be contributing to the discharge, right, or the flow due to this recharge. Okay. All right. So, what do we do? How do we handle this? Let me first say what we are how we can represent this situation. If you take a small strip, let us consider a small strip of length dr, all right. Let us say this distance is r and this thing is dr, all right. And if you look at this whole thing from the top, all right, if you look at this strip from the top, it will look like this. Okay. So, you have the radius is r and this is dr And what is this whole thing? This is basically your cylindrical shell. Cylindrical shell. Okay. So, if you are looking at from the top, it is a cylinder, but it is hollow at the bottom or in the middle. So, it is a strip. Okay. So, what we do is, let us consider the cylindrical cell. As shown. Okay. If we do that, then what is happening is, if you look here, the discharge at this location is, let us say Q, all right, and what we have said is, as we are approaching towards the well, the Q is increasing, right. So, let us say the discharge as we come out of this strip is Q plus dQ, all right. So, dQ is the discharge or the flow which is taking place due to the recharge that is coming in from the top, all right. So, we say let this dQ is what is the increase in the flow Q in the aquifer. So, dQ is the increase in the flow in the aquifer at some radial distance r. Why? Due to the recharge, okay, recharge that is taking place, all right. What will that be equal to? Okay, so, what will this dQ be? Well, it will be nothing but the velocity, all right, velocity of water at that point of time, at that location rather, times area, isn't it? So, what will that be? What is the velocity of water? It is the rate at which water is entering into this shell, right. W is the rate at which water is entering, all right. And what is the area across which it is taking place? Well, it is 2 pi r is the circumference multiplied by dr, right. So, this is the change, all right, and as we are going away from the well, or as r is increasing, Q will be decreasing, or this dQ will be decreasing, all right. So, we say, that is why we have taken this negative sign, all right. So, you say dQ is equal to minus of your 2 pi r W dr, okay, and we have taken negative sign, which basically indicates that as r increases, your Q decreases. As you are going away from the well, Q is decreasing, and if you are approaching towards the well, or R is decreasing, Q is increasing. Okay. So, just it is the notation part. So, then what we do is we integrate this quantity, integrate this equation rather, all right. Integration will give you what? You just do Q is equal to minus 2 pi, W is constant, the recharge rate, and then you have R dr if you will integrate, right. So, you will have r square by 2, okay, and then there is a constant of integration, all right. How do you find this constant of integration? Well, you use the boundary condition, and what is the boundary condition? At your r is equal to 0, or at the well, what is the Q? We are saying Q is equal to, let us say QW, right. So, that will imply what? You put Q is equal to QW here and R is equal to 0. So, your C will be equal to what? QW. Okay. So, that basically means then your Q is equal to minus pi r square W plus QW. Okay. This we will define as the equation number 7. All right. So, this is the relationship between Q at any distance r and the Q at the well, and how the W is constant and how the R is changing. All right. Now, this Q is what? This Q is the flow in the unconfined aquifer, right, and we have seen that earlier, that for the unconfined aquifer, right, what do we have? What is this Q? Well, this Q we had taken earlier as minus of your 2 pi r k times h dh dr. So, this is basically your velocity, all right, k dh k dh dr, and then 2 pi r h is your area across which it is flowing. Now, what is this Q? This Q we put from 7, okay, which is what? Minus of your pi r square w plus q w. Okay. Let us see, you go back, that is what Q is. Q is equal to, from equation 7, it is q w minus pi r square w, right. So, you just put that value of Q here and then you equate it to the right hand side, which will be minus of your 2 pi r k of your h dh over dr. Okay. Now, we separate the variables like we normally do, r on one side and h on the other side, okay, so that we can do the integration. All right. If you did that, you will have, and slight rearrangements, you will have 1 by r q w minus pi r w times dr, that will be on the left hand side, and on the right hand side you will have minus of your 2 pi k of your h dh dr. Okay. You can verify that, all right. Integrate it between the limits, all right. What you will get is this. I will not do the complete procedure here. Integration would yield you this h square minus h square will be equal to w over 2 k times what? Times r square minus r square, plus you have the q w divided by pi times k of your natural log of r over small r. Okay. So, you are using capital H and R as one boundary and general small h and small r as the other boundary. Okay. So, this is the equation of your water table profile and various other things which involves W with recharge and a pumping rate q w in a unconfined aquifer. Okay. So, this equation 8 is basically representing what? It is representing your profile, water table profile, all right, in which case, in the unconfined case where radial flow is taking place under steady state conditions and there is also recharge taking place W from the top due to rainfall or agriculture water or something like that, all right. So, this is a very important equation which can be used when we have the recharge taking place in the unconfined aquifer. Okay. So, if you look at a special case of this, we can determine what the discharge at the well would be, all right. So, equation 7 basically, or let me say equation 7 will give you at r is equal to capital R, what is q? Well, q is 0. At the radius of influence there is no flow taking place, right. So, if you use this in 7, what is the equation number 7? This one, all right. At r, small r is equal to capital R, your q is 0, the left hand side is 0, all right. That will give you the discharge at the well q w. Okay. So, if you did that, you will have 0 is equal to minus of your pi capital R square w plus q w, all right. That means your q w is equal to what? Pi capital R square w. That will be the pumping rate, or that will be the discharge at the well, which can then be used actually in this equation. Okay. Knowing the radius of influence and knowing the recharge rate, this can be put into this equation here, all right. So, you see that we can combine this equation 7 and equation 8, all right, to simplify our equation and get a composite relationship between profile of the groundwater table in unconfined aquifer under the recharge, all right, under steady state conditions. Okay. I would like to stop here as far as the steady state analysis is concerned. All right. The next thing we will do in this course is on the unsteady flow towards a well. Okay. We have seen after a prolonged pumping, when the steady state conditions are reached, how we can determine the drawdown and the groundwater table and the pumping discharge and so on. All right. However, in many of the aquifers, due to the permeability conditions or the characteristic of your aquifer, it takes a lot of time for things to become steady state. All right. So, it is very costly if let us say you are trying to determine the aquifer parameters. If the objective of managing your water resources is basically you have to first determine the aquifer parameters. To be able to use the steady state conditions, all right, you need the observations in terms of the drawdown. And if you are going to use the steady state conditions, then they will reach after a very long time. So, you have to pump the water for a very long time, which is not economical. Okay. So, we will use the unsteady state analysis, all right, to be able to manage our water resources or the aquifer system. Okay. So, let us move on and start looking at the unsteady state flow. Unsteady flow in a confined aquifer. Okay. So, we are no longer going to worry about the things to become steady state. All right. Okay. This we are actually going to look at very quickly. Okay. The governing differential equation in a confined aquifer. In the cylindrical coordinates, is given by the following equation. Okay. This equation we have actually seen earlier. We did the derivation of governing differential equations, all right, in the confined and unconfined aquifer. This we have done for the Cartesian coordinate system, all right, and then we had written down the equation for the cylindrical coordinate system. Okay. So, we will just take that equation as the governing differential equation, all right, and then we will see how it can be solved. All right. There will be couple of there are many solutions or the methodologies which has been proposed for this. However, we will be looking at only a couple of them. All right. So, let us look at the governing differential equation and one particular solution which is very famous and important in the groundwater hydrology is proposed by Theis. All right. So, we will look at that. Okay. So, first let us see the governing differential equation, which is described as this: del 2H over del S square. All right. We will not go into the details of the derivation of this, okay, is equal to S by T of your del H del T. Okay. All right. So, this is your governing differential equation, and then Theis proposed a solution to this governing differential equation with the following boundary conditions. Okay. I must point out that this is a slightly complicated equation as far as the solution is concerned. All right. So, the solution of this equation is extremely difficult using the analytical methodology, all right, or analytical solution is very difficult. Many numerical methods have been applied. However, Theis approached this problem under certain simplified assumptions or simplified boundary conditions and proposed a solution. The H is equal to capital H, that is your height of your piezometric surface at t is equal to 0 is equal to some capital H, all right, and that is number 1. And then what he said is that this height of the piezometric surface approaches towards the original value, right, when as your r tends to infinity, or you go very far away from the well when for the times which is larger than 0. Okay. So, under these boundary conditions he has obtained this solution as follows, okay, in which he defined the drawdown S as capital H minus small h, okay, is equal to q over 4 pi t of your integral from u to infinity of your e minus u over u du. Okay. And let us say if this is my equation 1, this is your equation 2, all right. We have renumbered the equation system for the unsteady case. Okay. This is written as q over 4 pi t of w u. Okay. So, this is the solution which was given by Theis to the governing differential equation number 1 under these boundary conditions, these ones. Okay. This equation is known as, this is called non-equilibrium equation. This equation is known as the non-equilibrium equation. Okay. Now, let me first define what is this WU. Okay. WU is a special mathematical function which is defined like this: integration from u to infinity of your e minus u over u du. Okay. It is called a well function. Okay. It is encountered in this kind of situation for aquifers or the wells, that is why it is called the well function in groundwater hydrology. And u is an intermediate parameter, all right, which involves time. Okay. U is something which is representing time and also the radial distance r. So, r square s over 4 capital T and small t. Okay. And let me say that this is actually like this. Okay. This is your equation 3, all right. You see that the combination of these equations 2 and 3, all right, this represents the complete solution to equation number 1, and this is called the non-equilibrium or any equation. Okay. Now, this well function W is something which is very difficult to obtain, all right. This W is a very complicated mathematical function which involves integration of e minus u over u du, all right, which is not easy to obtain, and many people have proposed certain approximate expressions or the Taylor series expansion of this WU, all right, and this is available actually in standard tables, all right. So, it is very difficult to find out the analytical value or the final solution. However, certain tables or the standard tables are available. Okay. What we will do is we will look at one simple expression which is based on the Taylor series expansion. Okay. This WU is defined as or can be expressed as this: minus 0.577216, it is a constant, minus natural log of u plus u minus u squared over 2 factorial 2 plus u cubed over 3 factorial 3 and so on. Okay. So, you see that we can consider a few terms in this expansion depending upon the accuracy which is desired, all right. So, this is the expression of your W which can be used in a computer program if we have to do this. Okay. Now, as I said earlier that this non-equilibrium equation is something which is applicable under the unsteady state condition, all right, when things are changing as a function of time. When you start pumping, the cone of influence or the cone of depression will be forming, which will be changing as a function of time, all right. So, if we can make certain observations in the observation well, all right, we can use these equations, all right, the solution which we have just obtained, and we can determine the value of the aquifer parameters, all right, which will be much more economical. So, people suggest that the non-equilibrium or the use of the non-equilibrium equation is much more efficient as compared to using the steady state equation for the determination of the aquifer parameters, all right, and we will look at a few reasons for that. The NE equation is used extensively, or very popularly I should say, to determine the aquifer parameters which is your S and T, okay. And then the why is that? The NE equation is better than the Thimes equation, which we had seen earlier, which is the equilibrium, also called the equilibrium equation, okay, for the steady state things, for steady state conditions, okay. Why? Because of the following reasons, okay. I am going to give you a few of them, okay. Number 1, S can also be determined, okay. You see that if we use the equilibrium equation or the equation for the steady state conditions, all right, we can only determine the transmissibility, all right. However, if we use the non-equilibrium equation, it allows us to determine not only the transmissibility T, but also we can determine the storage constant of the aquifer S, okay. The next one is that only one observation well is needed, okay. In the case of this non-equilibrium equation, we need to use only one observation well, all right. We will see that a little later in the course, okay. Number 3, the shorter period of pumping is needed. Shorter period of pumping is needed. Why? Because we are using under the unsteady state conditions which are in the beginning, or as you start pumping, initially the things are unsteady, all right. So, if you have an observation well, you can make the observation, you can note down the time and draw down etc., and we can apply these equations, okay. That means it is more economical. As compared to using Thimes equation, okay, because there you have to wait for the steady state conditions, all right. And number 4 is simple, that no assumption of steady state conditions, no assumption of steady state conditions is needed, okay. That is to say, we are assuming that the things are steady state. When we apply the Thimes equation to determine the aquifer parameters, we are assuming that things are steady state, but it is very difficult actually to attain the steady state conditions in real life, okay. So, because the things are going to be unsteady, all right, things will be fluctuating all the time, all right. So, it is difficult to obtain the steady state conditions. So, application of a steady state condition equation is actually will be violating the assumption if the conditions are not such, all right. That is why application of this non-equilibrium equation will give you better results, because there is no assumption involved, all right. So, we see that there are 3-4 advantages of using the unsteady state equation for aquifer parameters. I think I would like to stop at this point of time, and then we will come back and look at the solution of this equation. There are a couple of solution techniques to determine the groundwater table profile. Okay. So, we will come back and see a couple of other methods. Thank you.